What if I told you that the entire digital world, the shimmering screen in your hand, the invisible networks that carry our voices across oceans, the supercomputers predicting our weather, is all built on a fundamental, beautiful, and deeply flawed assumption? An assumption so pervasive we don't even see it anymore. It's the belief that our complex, messy, and unpredictable reality can be perfectly tamed, translated, and represented by a simple choice: a 0 or a 1. But you and I know that's not how life works, is it? Life isn't a clean switch, it's a dimmer. It's the grey area between the black and the white. In the grand theatre of nature, error isn't a bug, it's the engine of creation. A random mutation in a strand of DNA sparks a new species. A slip of the tongue reveals a hidden truth. A chaotic storm of neural firings in our brain gives birth to a symphony. Chaos is the messy, unpredictable, and glorious artist that paints the canvas of existence. So, this brings us to a question that could unravel the very fabric of modern technology. A provocation that is now shaking the foundations of Silicon Valley itself. What if, instead of building machines that desperately fight against chaos, we built machines that learn to use it? What if we could teach silicon to think not like a calculator, but like a storm? To understand where we're going, we first need to understand the ghost that has haunted our technology for 2 centuries. His name is Laplace's demon. Picture the early 19th century. The world was falling in love with a new idea: the universe as a grand, intricate clockwork mechanism. Every gear turned by another, every swing of the pendulum perfectly predictable. It was in this era of mechanical certainty that the French scholar Pierre-Simon Laplace conceived of a thought experiment. He imagined a vast intellect, a demon, so powerful that it could know the precise location and momentum of every single atom in the universe at one single instant. For this demon, Laplace argued, nothing would be uncertain. The future, like the past, would be present before its eyes. It could predict the next roll of the dice, the path of a falling leaf, the rise and fall of empires, all with absolute, unerring certainty. There would be no mystery, no chance, no free will, only the relentless, grinding gears of cause and effect. This vision of total, perfect control became the philosophical bedrock of computation. The machines we built were designed to be miniature versions of Laplace's clockwork universe. We demanded perfection. We gave them a precise input, and we expected a precise output every single time. A single flipped bit, a single miscalculation, was seen as a catastrophic failure. The demon of perfect predictability was embedded in the heart of every processor, every line of code. It was a beautiful, elegant, and powerful vision. And for over a century, it was the only vision we had. But it was a vision that mistook a perfect model of the world for the world itself. And in doing so, it blinded us to a much deeper, more powerful truth. Just as the Laplacian dream reached its zenith, a Russian mathematician named Andrei Markov began to challenge it from the inside out. He was a man fascinated by what others dismissed as noise. He looked at the seemingly random sequence of vowels and consonants in a Pushkin poem. He listened to the fluctuating notes in a piece of music, and he saw something that Laplace's deterministic view missed entirely: a pattern hidden within the chaos. Markov didn't believe in pure, meaningless randomness. He proposed that even chaos had its own logic, its own set of rules. His breakthrough was deceptively simple. The probability of what happens next often depends on what just happened now. In a sentence, the word "that" is far more likely to be followed by a noun like cat than by another "the." The current state influences the future state, not with certainty, but with a measurable probability. This gave birth to the Markov chain, one of the most powerful tools in modern science. It was the first great step toward taming the unpredictable, not by eliminating it à la Laplace, but by understanding its internal rhythm. It allowed us to transform what looked like a random mess into a structured, statistical model. You experience Markov's legacy every single day. The predictive text on your phone that uncannily guesses the next word you want to type? That's a Markov chain at work, calculating the probability of the next word based on the last one. The way a streaming service recommends your next song? That's Markov's ghost, whispering the statistical likelihood that you'll enjoy it. Andrei Markov didn't kill Laplace's demon, but he landed the first major blow. He showed us that the world wasn't a perfect clock, but it wasn't a meaningless lottery either. It was something in between, a dance between order and chance. The next great leap came not from a quiet study, but from the heart of the most secretive and high-stakes scientific endeavor in human history, the Manhattan Project. The scientists at Los Alamos faced a problem of terrifying complexity: how to calculate the behavior of neutrons in a nuclear chain reaction. The path of a single neutron was fundamentally unpredictable. It could be absorbed, it could fly off into space, or it could hit another nucleus and fission, releasing more neutrons. Trying to calculate every possible interaction for trillions upon trillions of particles was an impossible task, far beyond the capabilities of any human or machine. Laplace's demon would have been stumped. It was here that a brilliant Polish-American mathematician named Stanislaw Ulam had a moment of profound insight, supposedly while playing a game of solitaire. He realized he didn't need to predict the exact path of every single neutron. He just needed to know the average outcome. What if, instead of trying to solve the impossibly complex equation, they just simulated the process over and over again, using random numbers to decide the fate of each individual neutron? He took the idea to the legendary John von Neumann, who immediately saw its power. Inspired by the casinos of Monaco, where Ulam's uncle used to gamble, they named it the Monte Carlo method. It was a radical departure from traditional mathematics. It was, in essence, using chaos as a tool to understand chaos. Instead of demanding a single, perfect answer, they ran thousands of randomized simulations, thousands of virtual atomic gambles, and looked at the statistical pattern that emerged. Pela primeira vez, o caos virou ferramenta científica. For the first time, chaos became a scientific tool. They had learned to ask the universe a question, not by demanding a single answer, but by listening to the average of 1,000 whispers. While the world was celebrating the birth of the first digital computers, enormous room-sized behemoths of vacuum tubes and relays, John von Neumann, the very man who helped create them, was already seeing their fatal flaw. He saw that the relentless pursuit of absolute precision was a dead end. He looked to the most powerful and efficient computer ever known for inspiration: the human brain. Our brain is not a pristine digital device. It's a warm, wet, messy, biological machine. It operates in a constant storm of electrical and chemical noise. Neurons misfire. Connections are imperfect. And yet, from this biological chaos emerges thought, creativity, and resilience. The brain doesn't need to be perfect. It just needs to be good enough. It learns from its errors and adapts to uncertainty. This led von Neumann to propose a truly revolutionary idea, decades ahead of its time: stochastic computing. The word stochastic simply means having a random probability. He envisioned machines that didn't fight noise but embraced it, making it part of the calculation itself. These machines wouldn't represent the number 5 with a perfect, unchanging set of bits. Instead, they might represent it with a stream of random pulses that on average fired 50% of the time. The idea was mind-bending. He was proposing computers that wouldn't have to be right every single time. They just had to be right on average. They would be less precise, yes, but also far more efficient, resilient, and, in a strange way, more intelligent. He was suggesting that the future of computing lay not in being more like a calculator, but in being more like a brain. It was a prophecy that almost no one was ready to hear. Von Neumann's vision was so radical that it remained a theoretical curiosity for years. But a prophecy is nothing without a prophet willing to bring it to life. That prophet was a British engineer named Bernard Gaines. In the 1960s, inspired by von Neumann's writings, Gaines embarked on a quest to build the world's first truly stochastic computer. He called it the Russell. The Russell was unlike any machine built before. It didn't just tolerate noise, it literally used it as a computational resource. Its logic gates were designed to work with probabilistic streams of bits, not definite zeros and ones. This gave it an almost biological resilience. If a few of its components failed or became unreliable, a common problem in the early days of electronics, the Russell didn't crash. It just kept on working, its answers becoming slightly less accurate, gracefully degrading instead of catastrophically failing. It was the first glimpse of a machine that was imperfect, adaptable, and fundamentally robust. But the world was moving in the opposite direction. The digital revolution was in full swing, and its mantra was Moore's Law. More transistors, more speed, more precision. Or, Gaines's stochastic process, while elegant, was agonizingly slow compared to its digital counterparts. For the problems of the day, a fast, precise, but brittle machine was seen as far more useful than a slow, approximate, but resilient one. In 1978, the project was abandoned. The Russell was dismantled, and von Neumann's vision was relegated to the footnotes of computer science history, forgotten for nearly half a century. The path of chaos was abandoned for the superhighway of digital perfection. For decades, the path of digital perfection seemed limitless. Moore's Law held true, and computers became exponentially more powerful. We built a global civilization on the promise of faster, smaller, and more precise chips. But in the 21st century, we have finally hit a wall built of physics and economics. In our relentless quest for precision, we've shrunk transistors down to the atomic scale. They are now so small, just a few dozen atoms across, that the bizarre and chaotic rules of quantum mechanics have started to interfere. Electrons can now spontaneously tunnel through barriers they shouldn't be able to cross, flipping a 1 to a 0 by sheer quantum chance. The very chaos of the universe we tried to eliminate is now leaking back into our perfect machines. To combat this, we have to build ever more complex and power-hungry systems to ensure perfect fidelity. This has led to an energy crisis of colossal proportions. The modern data centers that power our cloud, our social media, and our AI are energy vampires. Together, they consume more electricity than entire countries. The energy required to cool these massive server farms, to keep the demon of Laplace happy and the calculations perfect, is becoming environmentally and economically unsustainable. The relentless pursuit of absolute precision has become its own undoing. And so, in the face of this crisis, the world is beginning to dig through the archives, searching for that forgotten path, that abandoned prophecy of a machine that works with nature, not against it. And that is where our story takes its most exciting turn. In a world struggling with the limits of precision, a startup named Normal Computing has emerged, and its mission is to invert the entire logic of the computer industry. Their philosophy is simple and profound. If you can't beat the noise, join it. In fact, why not use it as the very fuel for your engine? Instead of spending billions on designing chips that eliminate every last bit of electrical noise and quantum uncertainty, their engineers are building chips designed to live on the edge of chaos. They operate their hardware in a near-threshold state, a delicate physical regime where the transistors are so sensitive that their behavior is inherently unpredictable. A tiny fluctuation in temperature or voltage can cause them to flip randomly between on and off. To a traditional computer designer, this is a nightmare. It's the definition of a broken chip. But for normal computing, this is the magic. This unpredictability is precisely what makes their processor so powerful. They have stopped trying to force the physics to obey the math. Instead, they have found a way to let the physics do the math. The chaos isn't a problem to be solved. It has become the method of solution itself. So how does a computer that thinks with chaos actually work? It requires a complete shift in our understanding of what a number is. In a digital computer, the number 7 is represented by a fixed, static pattern of bits. 0, 1, 1, 1. It is always 0, 1, 1, 11. In a stochastic chip, the number 0.7 isn't a static value. It's a dynamic process. It's represented by a random stream of ones. And zeros, where over any given period, 70% of the bits are ones and 30% are zeros. The number is encoded in the average of the flow, Not in any single bit. This is where the true elegance lies. To perform a complex mathematical operation like multiplication, you don't need intricate, power-hungry circuits. To multiply 0.7 by 0.5, for example, you simply take the two random bit streams representing those numbers and pass them through a simple AND gate, one of the most basic components in electronics. The resulting output stream will, by the laws of probability, naturally average out to 0.35, 70% of 50%. It is calculation as nature would do it. The answer emerges organically from the interaction of two chaotic flows. The noise isn't a flaw, it's the medium carrying the information. The precision we seek is born directly from the heart of uncertainty. It's a system where every error, every random flip of a bit, isn't a mistake, but a vital part of a larger, coherent, and incredibly efficient calculation. For decades, modern engineering has been obsessed with eliminating the unpredictable. We build bridges with massive safety margins. We write software with layers of error checking. But the most sophisticated object in the known universe, the human brain, proves that intelligence can arise directly from chaos. Your thoughts, your memories, your very sense of self are not the product of a precise digital calculation. They are the emergent harmony of billions of neurons firing in a seemingly erratic, noisy, and probabilistic storm. Each neuron is an unreliable component, yet together they create a system of unparalleled creativity and resilience. Now consider the most advanced artificial intelligence of our time. Models like DALL-E or Midjourney, which can create breathtaking art from a simple text prompt, operate on a principle that is deeply, fundamentally chaotic. They start with an image of pure, random noise, like the static on an old television set. Then, guided by the prompt, they slowly and iteratively refine that chaos, nudging the pixels step by step, until a coherent and beautiful image emerges from the noise. And here lies the great irony of our time. We are using perfectly precise, energy-guzzling digital machines to simulate a chaotic, creative process that they are inherently terrible at. The software, which needs chaos to learn and create, is at war with the hardware, which was built to destroy chaos at all costs. The work of normal computing isn't just about building a better chip. It's about healing this fundamental rift, about creating hardware that speaks the same native language as the AI it is designed to run. The ultimate goal of this revolution is to finally align the body of the machine with the soul of its intelligence, to create chips that think in the same probabilistic way that AI learns. This shift represents more than just an engineering upgrade. It heralds the birth of a new language for interacting with technology. For a century, to program a computer meant to provide it with a set of rigid, explicit, step-by-step instructions. It was a monologue where we dictated orders and the machine perfectly obeyed. The future is a dialogue. Dominating artificial intelligence will no longer be about writing flawless code. It will be about learning how to converse with chaos. It will be about becoming a guide, a teacher, a curator of a probabilistic system, gently nudging it, providing it with the right data, and understanding its emergent logic. The masters of this new era will not be the programmers who can write the most precise algorithms, but the thinkers who can best understand the rhythms of probability and the art of adaptation. It is the beginning of an age where true mastery of technology means letting go of the illusion of absolute control and learning to dance with the beautiful uncertainty of the system itself. This shift towards stochastic computing is more than a technical innovation. It's a profound philosophical evolution. It's about our society making peace with uncertainty. For centuries, inspired by Laplace, we have chased the ideal of perfection, of a world without error. We've tried to optimize our lives, our businesses, and our machines to eliminate every trace of unpredictability. Stochastic computing suggests a different, more mature path, a search for a healthy balance between order and disorder. In this new world, the single, perfect, calculated answer ceases to be the ultimate goal. What matters is the process of observation, of waiting and watching until a stable pattern emerges from the noise. Think about it. This is how nature has always worked. A forest doesn't grow according to a perfect blueprint. It emerges from the chaotic interplay of sunlight, water, and millions of individual organisms. A wise decision isn't a single calculation. It's the result of observing patterns over time, weighing probabilities, and trusting our intuition. That magnificent, biological, stochastic computer in our heads. Technology, it seems, is finally starting to learn the same lesson that nature has been teaching us all along. While the processor from normal computing is still in its experimental stages, its core logic opens up a new paradigm for science and technology. By fundamentally accepting uncertainty as a feature, not a bug, it brings the cold, hard logic of Silicon one step closer to the warm, adaptive chaos of biology. Imagine what becomes possible with computers that can truly think in probabilities. We could create climate models that aren't just predict a single outcome, but can explore the entire landscape of possible futures. We could design new medicines by simulating the fantastically complex and chaotic dance of protein folding in a way that is currently impossible. We could build economic models that understand the animal spirits of the market, not as an error to be ignored, but as a fundamental part of the system. These are machines that can err, adjust, and learn in real time, just like a human brain. This fusion of order and chaos could redefine entire fields of human endeavor, allowing us to build machines that can finally comprehend the deep, unpredictable, and probabilistic nature of the universe as the universe itself does. And so, we arrive at the final, most human lesson of this entire journey. Perhaps the next great technological leap will not come from machines that are faster, more powerful, or more perfect. Perhaps it will come from machines that are, in a sense, more human, more flawed, more adaptable, more comfortable with being wrong. Perfection, we are learning, is a cage. It limits, it constrains, it demands an unsustainable amount of energy to maintain. Error, on the other hand, is what liberates. The human brain creates because it is flawed. A mistake in our thinking leads to an unexpected connection. A glitch in our memory sparks a new idea. Our creativity is born in the space between what we intend and what we accidentally discover. When our technology finally learns to embrace its own inherent chaos, to see the glitch not as a failure, but as a feature, perhaps we, in turn, will learn to do the same for ourselves. Perhaps we will begin to understand that the true meaning of intelligence isn't about control. It's not about forcing the world to conform to our perfect models. So I leave you with this to ponder. Where in your own life have you been fighting against chaos when you could be dancing with it? Have you ever had a mistake, an error, or a moment of pure chance lead you to something wonderful and unexpected? Share your story in the comments below. I'd love to read it. Thank you for joining me on this journey into the heart of a new machine. I hope it sparked something in you, as it did in me. And if stories like this, that challenge the way we see the world, are what you're looking for, please consider hitting that subscribe button and joining our community of thinkers. It helps us continue to explore these big ideas together.